This is video 15 in the thermodynamics course with Lars Erik, and we are in subchapter 11.6 in the textbook, and the topic is the fundamental residual property relation. I start with a closed system. And I hope this one should be familiar to you. It's the relation between Gibbs free energy and volume, pressure, entropy, and temperature. This is equation 6.6. And if we divide this by RT, we get dNG over RT equals NV over RT dP minus NH over RT squared. This is 637. There is some manipulation to get from here to there, about 31 equations in chapter 6, but this is also a traditional equation when it comes to change of Gibbs free energy with pressure and temperature, and this equation is dimensionless. Ng is energy and RT is energy. For an open system, we have started with a closed system. We only changed pressure and temperature. Now we are going to change the amount of each component. This is the same as fix 37, but now we also add some components, and when we add some components, then we must multiply with the partial molar Gibbs free energy, and we have divided all the equation with RT. And this is 11.4. This equation 11.54 is general. This equation just states this one, which is also general, and we just add more amount of each component, and then this is the proportionality factor when we are adding more components. Because it is general, it must be valid for ideal gas. So the Ig over RT equals NVIG. I just put superscript Ig on all the properties. And again, we sum up the ideal gas partial molar property. And if we now want an equation for the differential of the residual gives the energy over RT, that is the difference. A residual property is the difference between the actual property and the ideal gas property. And here we have one general equation for a property, and this is the equation for the case of ideal gas. So for a residual property, it should be the difference between that one and that one. And when I'm writing, I'm just changing the superscripts. So then we end up with 1155, and we can do the same, and then just replace this with an expression for the fugacity coefficient. The fugacity coefficient is directly related to the partial molar residual property, like this. And then we have 1156. And as a result of this, and these are theoretical equations, and we are manipulating them, but I am after a result that we can make use of. And the logarithm to the fugacity coefficient can then be the partial derivative of mgr over RT by the all other components except I constant. And this equation can be used to calculate the fugacity coefficient of a component in a mixture. And that can be used by using, for instance, an equation of state. So what I have gone through here is just to define or establish a fundamental residual property relation. The starting point is the general equation connecting Gibbs free energy, volume, pressure, entropy, and temperature. We make it dimensionless. We extend this to an open system. We state that we add some components, and then we add the amount of Gibbs free energy that is actually directly connected to the change in the amount. Then we just state that this is very general. Then we say that this is valid for an ideal gas because it is general. Then we have already defined the residual property as the difference between the actual property minus the ideal gas property. And then we get this fundamental equation for residual Gibbs free energy, which is 1155. If we also make use of the definition of the fugacity coefficient for a mixture, we can replace the last term with the sum of the logarithm to the fugacity coefficient of each component. And this is, say, just theory. And then to indicate that there is a direct application here, we can use this to say that the logarithm to the fugacity coefficient is the derivative of the residual Gibbs free energy with the amount. And then if we are interested in the fugacity coefficient for a component, and I am interested in that because that is a direct measure of the non-ideality of the component in the gas, and that can be calculated, for instance, by the use of an equation of state. That is the end of video 15.